Okay, so this is a continuation of the problem that we had started in the previous video, and that problem included a 50 kilogram kid sitting on a wheelie chair, and a person applies a force to the kid through one revolution, and then after that one revolution the kid pulls his arms in, and in each arm, in each hand really, not in the arms, that would be terribly unpleasant, he pulls the masses in each hand in close to his body, so that they go from a distance of 0.75 meters away to 0.2 meters away. And I had calculated the moments of inertia for the initial state, which is right here, and for the final state, which is there. And these are of course different moments of inertia. And this is done, this pulling in of the arms is done without the aid of any external torques. And so I'll just make a little note here. So no external torques means this is true, that we have this conservation of angular momentum. And at that point I decided, in the time that you couldn't see when I can magically do things without you seeing it, I decided we needed some diagrams to help make sense of this a little bit more clearly, because I really ran into a problem where I had this initial angular velocity of 0, which corresponds to this picture here, and what's happening in this picture is, here's the kid. This is a top-down view of our cylindrical kid with the massless spindly arms, and in each hand there is a mass, a distance r1 away. And the force is applied to one of the hands perpendicular to the lever arm. So we have this force perpendicular to the lever arm, and we should then be able to figure out what happens after one revolution. So here's the one revolution later. I'll put some dots leading to it and some dots away. So we've kind of got this kid in the act of just finishing up with that force being applied. And now this kid has an angular velocity. And I'm going to call this angular velocity omega b. And so I'm going to update this to be omega b. And I'm also going to update these omegas to be omega b and omega c. So this kid has just finished the one revolution, is now going at omega b. And then immediately, instantaneously, which is a remarkable feat to go from out here instantaneously to in here, instantaneously changes his moment of inertia and is now going at omega c. One of the nice things about this conservation of angular momentum is that it actually doesn't care whether this was done instantaneously or not. It could just as easily be now the kid finally, after rotating through over pi over 2 radians, is now in. So this is a little bit unrealistic. This one's maybe a little bit more realistic. So it doesn't have to be an instantaneous change. The nice thing is this equation doesn't care about the details of how we go from here to here in terms of the moment of inertia. It just cares that the moment of inertia has changed like that. So with the diagrams, it at least helps me to see that, in order to figure out what this is, ultimately how fast is this kid rotating, I'm probably going to need to know how fast the kid is rotating after the force has been applied. So my first issue then is to tackle this A to B range. And that's where a lot of my givens are for here. The theta 0, or theta naught and theta. This is really, if I'm being careful about this, I'll call this A now, and I'll call this B. I'll call that A, and that B, and this is the angular acceleration from A to B, and so on. So what I'm going to do then is I'm ultimately trying to find for this from the A to B phase. Okay, this guy right here. But in order to do that, I'm either going to need to know time or the angular acceleration. And we dealt with these types of problems, these kinematics forces blends, back when we were studying forces. And this is no different. Only now, instead of sum of forces equals m times a, we're going to be dealing with something a little bit different. We're going to be dealing with, and that's actually a little bit hard to see. Let me use a different color. We're going to do sum of torques equals I times alpha. And so the torque that's involved is R1 times our force equals the moment of inertia, and it's our original moment of inertia. So it's this guy right here, this 2m1r squared. So we have 2m1r squared plus 1/2 mr squared, big M r squared. Sorry, that's r1 squared, plus 1/2 big M, big R squared, and all of this is times alpha. So to solve for alpha then, all I need to do is a little bit of algebra. And I divide by 2m r1 squared plus 1/2 big M r squared. So basically the torque divided by the moment of inertia. And we somehow actually, one thing you might be wondering is that really the only torque acting on it, this force that's being applied to the hand? And realistically, no, that wouldn't be the only torque. Most wheelie chairs have this thing called friction that would prevent it from spinning absolutely freely. But we happen to have this remarkable frictionless wheelie chair that's going to allow us to spin without slowing down once we get up to a certain speed and with no resistance to forces. The reason why you know that is because we're not given any indication that there is friction. So realistically, no, this would not be the only torque. There would likely be, if you can imagine, that somewhere in here there is a shaft where the wheelie chair is attached to the base, and this is the shaft about which the whole chair can rotate. So there would probably be some sort of a frictional torque acting counter to the force on the hand. Not very effectively, and it could actually be a larger force vector than this, but because the radius vector would be quite low, we'd have a distinct advantage by pushing out here. In any case, we get this angular acceleration, and now what we can do with that is we can finish off the kinematics problem. We now have this angular acceleration. We can go ahead and we can solve for this using the no t equation. So what that's going to look like is, let's use some yellow, see how that looks. We'll use the no t, so we have omega squared equals omega naught squared, and by the way, this is omega at stage B, right after the push has been removed, equals omega at point A squared, plus 2 alpha delta theta. And our delta theta is, of course, 2 pi, and we know what alpha is, and we know that this is 0. So we have omega b equals the square root, and this is unfortunately going to be quite long, 2 times, and we'll get some nice purple and yellow going on here, 2 times the mass in his hands times how far away they are originally squared, plus the moment of inertia of the kid himself. All of this times 2 pi r. Because the person has gone through, oops, actually not 2 pi r. I'm not looking at distances here, times 2 pi. Did I do that? Yep, I did that right up there. So we have all of these things, multiply them together, and take the square root, and that'll give us our actual angular velocity after the force has been applied. Okay, and for those of you who absolutely cannot stand to wait until the end to see what a number is, we can throw in some numbers here. This is a lot of math stuff to look at. So we'll have 2 times 1 times 0.2 squared plus 1/2 times 50. Oops, actually that's 0.75 squared plus 1/2 of 50 times 0.2 squared. All of this times 2 pi, and we'll square root that. And I got something like 5.17 radians per second out for this. Now that's less than 1 revolution every second, so this isn't really fast. This is kind of slowish, but it's still, with the arms outstretched, is still a decent speed. And this is not our final answer. To get our final answer, what we have to do is now we apply this. So I kind of identified early on that this was going to be a conservation of momentum problem at its heart at the end, and that was because there was a change in the moment of inertia. Right, we had the arms out, then we had the arms in. So it's much less resistance to change in motion when the arms are in. Or, I'm sorry, not change in motion per se, but rotation when the arms are in than when they're out. So when we suddenly pull the arms in, we have to maintain the same amount of rotational motion. because there's less stuff out far, there's less stuff moving through a great distance at any given time. So this stuff, this body here, is only moving through a fairly small distance at any given time. So what we need to do now that these are in is we need the whole thing to rotate at a greater speed than it was before. And that's the only way that we can conserve that quantity of angular momentum. So I'll start this over again a little bit, and we'll have omega at B, L at B equals L at C. We'll have moment of inertia at B times omega B equals moment of inertia at C equals, or times omega C. And we know what all these things are already. We already know what our I's are in terms of the quantities that are involved. I've solved for them up here. Okay? And so then it's just a matter of putting those down. And I happen to know that the moment of inertia at B is 2.125, and the angular velocity we saw for that about 5.17. And at the end, with the arms pulled in, we actually basically have the moment of inertia of the system down to 1.08 kilograms meters squared. And that leaves us the ability to find out what this omega c is. So we just do a little bit of division. Okay, and what we end up then with is, once we finish that up, we get about 10.2 radians per second as the final speed. So we have a little bit over 1.5 revolutions every second now. So we went from, not actually, closer to 2 revolutions every second. So we went from less than 1 revolution every second to a little bit less than 2 revolutions every second because of that change in the moment of inertia. So this is the answer to the question, and this is how you would set it up. You would set up your givens just like you would for any problem that we've done previously. The difference is that the mass is a little bit trickier to deal with because when it changes locations, you have changes in the moment of inertia. Use pictures whenever possible to try to help organize yourself, and then start solving for the things that you know. Come up with a plan. And so in this case, the plan was to get to the point where I could use conservation of angular momentum. And in order to do that, first needed to figure out what the angular acceleration was while the force was being applied. And once we had that, we could use that to find, using angular kinematics, we could use that to find the angular velocity after the person would have just after the force stops being applied. And then we use conservation of angular momentum once that external torque caused by the force F is removed.